Good morning, campers. All right. Sun's up, snow's on the ground. It's got to be an exciting day. So today we're talking about the G of Y method. This is a technique. So this technique is something that is mentioned fleetingly in the book at this point, and is going to become more substantial as we go along. And we want to use this method when we're curious about what could another distribution look like if it has a dependence on one that you already know. So a new distribution from an old distribution. Now, we saw that already when we interpreted Poisson in a general setting, and we got the gamma distribution. But that question was really a change, a reversing of questions. Rather than a fixed time and when something happened, we said, well, how many things happened in some period of time? So it was a dependency, but it's not the G of Y technique. It just relates how they go together. So let me demonstrate this method. And this method is based upon the idea that you know what a cumulative distribution is. So they call it the cumulative distribution function, which is the probability that some random variable is less than or equal to a specified value x. That's your cumulative. And you know darn well that if it's a finite support, it's going to start at 0 someplace and somehow rise up to 1, and it would look something like that. Now, if it's an infinite distribution, then it will rise from 0 at minus infinity and get 1 at infinity. And there are many functions that could do that. Like here would be such a looking distribution. Arctangent kind of looks like one of those possibly infinite CDFs. But the beauty of the CDF is when you take its derivative, you get the distribution function. So let's start with a very simple function. I'm going to take the world's simplest function that's continuous. I'm going to let f of x be uniform 0, 1. Now the picture of the distribution extended to the real line is just a bump between 0 and 1. I'll drop the hat and just refer to f of x as being 1 on 0, 1. Now what I'd like to do is to define a new random variable by doing a functional association between the x values that come out of a random variable x with some other value. So for example, I might square every value that comes out, or I might cube it, or let's do the following. Let's let y be a new random variable, which I'm going to do is 3 plus 7 times the old random variable x. Now, I can philosophically argue this pretty simply. We know that x varies uniformly from 0 up to 1. So that means I'm pretty certain that 7x varies uniformly from 0 up to 7. And now I'm pretty certain that y will vary uniformly from 3 to 10. But that's an argument using descriptive words. It's not the mathematically sound argument. So now I'm going to use definitions and show that indeed y is uniform 310. So I'm going to prove that. And this is the G of Y method. We're going to use G of Y a lot. So first off, we're going to say x is uniform 0, 1, and y is 3 plus 7x. And now I'm going to define G of y, which is the cumulative distribution, which is the integral from minus infinity to little y of that f of t dt, where this is my f describing y. But the beauty of the G of y is that I don't necessarily know this f of t, but the g prime of y will be f of y, and that will be the f describing y. So if I can calculate this integral without knowing f, I could take its derivative. Now, how can you calculate an integral without knowing f? Well, the answer is there's an alternate description of the cumulative distribution. It is the probability that y is less than or equal to some little fixed y value. So now you need to imagine that the y is fixed, the little y. And now let's plug in what capital Y means as a random variable. It is 3 times the random variable x, less than or equal to some fixed number. But this equation has several interpretations. One is that it's the same as saying x less than or equal to y minus 3 over 7. So what is the probability that a value of the random variable x is less than or equal to y minus 3 over 7? Well, off to the side, let's not worry about the y. What's the probability that x is less than or equal to half, or the probability that x is less than or equal to 3/4, or the probability that x is less than or equal to minus 1, or the probability that x is less than or equal to 12? How hard are these? Well, these are all integrals of the uniform function on 0, 1, and we know this answer. This is 1/2, because this is the integral of the uniform function from minus infinity to 1/2. The only part that matters is from 0 to 1. And this one is 3/4, because it's the integral from minus infinity to 3/4, but we only pick up the 0 to 3/4 part. This is 0, because the integral of the uniform function from minus infinity to minus 1 is 0, because the uniform distribution function 0, 1 is 0 in that region. This answer is 1. All of these are integrals of a known function. These are the integrals from minus infinity to some alpha of 1 dx, which will be x evaluated from 0 to alpha, because from minus infinity to 0, the function's 0. This should have been the uniform function. So it's only going to be 1 dx. X from 0 to alpha. So the answer is alpha if alpha is in 0, 1. If alpha is less than 0, the answer is 0. And it's 1 if alpha is bigger than 1. So we know how to do this. So let's go over here and call this alpha. So the probability that x is less than or equal to some alpha is the integral from minus infinity to alpha of the uniform distribution 0, 1 dx. And this function is 0 to the left of 0, plus it's the integral of 1 up to there. And if alpha is greater than 1, it's just going to be 1. So this integral is just alpha. So we get alpha when alpha is less than or equal to 1, greater than or equal to 0. We get 1 when alpha is greater than 1. And we get 0 when alpha is less than 0. Well, what is alpha? Well, alpha is this. So g of y, is what we've been calculating, is just alpha, or 1 or 0. So g of y is 0 when, now what was alpha? Alpha was y minus 3 over 7 is less than 0. That's the answer. The answer is y minus 3 over 7 if 0 is less than or equal to y minus 3 over 7 less than or equal to 1. And it's 1 if y minus 3 over 7 is greater than or equal to 1. So there's our answer. I want to write this in a different way. So g of y is 0. Well, what does this say? If y is less than 3. What does this say? It says if y is bounded between 10 and 3, the answer is y minus 3 over 7. And what's this say? It says if y is greater than or equal to 10, it's 1. These actually all match up at 3 and at 10. So now I can calculate g prime of y. G prime of y is 0 for y less than or equal to 3. G prime of y is 1/7 for y in the interval from 3 to 10. And it's 1, 0 for y greater than or equal to 10. And we have just proved that the distribution of y is the uniform function on 3, 10. So y is uniform 3, 10. This is called the G of y technique. You convert a probability statement about a y with a fixed value into a probability statement about x. Convert that inequality to an equivalent statement about x and view your y's as fixed values. Then you evaluate your known integral, whatever the distribution of x is known to be, carefully evaluate it and come up with your g of y, and then take its derivative and you have a description. Now, some of these problems are kind of sneaky. If you want to go and practice one, why don't you do try y equals the max of, let's say, 2 and x when x is, let's say, uniform 1/11. That's kind of sneaky, but I think you can do the integrals and set it up. Another one you might try is y equals x squared when x is, let's say, uniform to 3. Let's see if you can work through those integrals. We are not going to explicitly have a test on this type of material for the next one, except for the example I just did where y is a linear transformation of a known a known x distribution. So that y equals mx plus b is a very simple one to manipulate. So you might consider this, well, I'll do one here in just a moment. So, all right, so there's our G of y technique. Woohoo, now comes a great topic. Here's my first question. Are you normal? You ever wondered about that question? Ever taken one of those cosmopolitan quizzes to find out if you're dating the right person or if you're smart enough for your mate? Or you ever taken one of those quizzes of which Harry Potter character are you? Oh my goodness, there are tons of questions that can be asked about who you are. How would you be described? Human descriptive statistics are such simple things as a 6-foot-tall male, blonde hair, blue eyes. But what are the descriptive statistics inside of mathematics? Well, X bar is an average of a sample. Mu is the average in the entire population. S is the standard deviation of a sample. Sigma is the standard deviation of an entire population. These are descriptive statistics, as are quartile 1, the median, and quartile 3, the min, and the max. We have got lots of things that describe things. Heck, we can take Q3 minus Q1, which, if you remember a box and whisker plot, that describes guaranteed to be the range of the middle 50% of the population. So maybe that's what we should call normal. If you land in here, you're normal. But what variable are we measuring? Are we talking about height? Are we talking about your weight? There's a million questions we can ask that produce a measurable statistic, and that measurable statistic then produce a quartile 3 and a quartile 1, and what do? We take the difference and we declare you to be normal. But that seems arbitrary. Sure, it's arbitrary. But does it make sense to say that the middle 50% of the world are the normal people, and there's the people above normal, 25% the people below normal? I think this is a very natural definition of normality. Let's shoot for that. Can we come up with a definition that works in this way for any distribution? Well, before we do that, let's see if we can find a distribution that seems to overlay on top of reality well. What do I mean by that, to overlay on top of reality well? Well, first off, it turns out if we draw lots of distributions, they have a habit of often being symmetric, but not exactly so. They have a habit of being unimodal, one hump, and they have a habit of having this shape, this one-humped shape. Now, mathematically, if you can write down something that looks like that, then you've succeeded in creating a shape like that, but there are many, many shapes that look like that. So what properties do we want some function that has this shape? Well, first off, it turns out that this function arises naturally. And that's a dangerous word in mathematics, to quote the word natural or the word trivial, because often there may be some deep philosophy or deep steps behind it, but at the moment when you said it, it was easy to do or it was obvious. That's not easy to formulate mathematically. It's something that's trivial or something that's obvious or something that's, quote, natural. However, I'd like to point out that there's something pretty easy to be done. Let's start. I want to make a very small sample set. I'm going to make a sample set of the heights of a couple of people. And I'm going to use a strange unit so the numbers are very reasonable. So I've got a 3. Oh, this is not a set. This is a list of data. I've got to be careful here because I'm going to repeat some numbers. So we got a 3, a 3, a 4, a 4, a 4, a 5, and a 7. Here is our individuals in our data set. And if I were to graph it, I can actually graph it quite nicely with just one unit at a time. There's my graph of the data. In fact, it looks quite unimodal, looks fairly symmetric. Now, what I'm going to do is I'm going to start grabbing people in groups and measuring their height, but I want one piece of data from that group, so I am going to create averages of my data. So let's, from this set, create subsets of size 2. So here we go. We got 3, 3, 3, 4, 3, 4, 3, 4, 3, 5, 3, 7. Then we get that exact same list here, except without that 3, 3. So we have 3, 4, 3, 4, 3, 4, 3, 4. Oops, too many 3, 4s. 3, 5, 3, 7. And now I have 4, 4, 4, 4, 4, 5, 4, 7. Then I have 4, 4, 4, 5, 4, 7. Then I have 4, 5, 4, 7, and then I have 5, 7. So if I was to sample 2 at a time from this universe of a set called, this list called S, what kind of data could I create? Well, I can create these doubletons, but I'm going to create an average from them. So now, average of 3 and 3 is 3, 3 and 4 is 3.5, 3.5, 3.5. Average of 3 and 5 is 4, 3 and 7, 10 is 5. Got this one. Now this will be 3.5, 3.5, 3.5, 3 of those again. That'll be another 4 and another 5, and the average of 4 and 4 is 4, 4. Oh, and we have a 4.5. Average of 4 and 7 is 5.5, and now we have another 4 another 4.5, and another 5.5, another 4.5, another 5.5, and then finally a 6. So now I have a long list of data. I'm going to write that out. 3, 3.5. And how many 3.5s are there? 1, 2, 3, 4, 5, 6 of them. How many 4s at 1, 2, 3, 4, 5 if I did it right? And I've got, looks like 3 4.5s, 2 5s, 3 5.5s, and 1 6. So if I sample 2 people at a time from this group of individuals and then record their average, this is what I get. What does its histogram look like? Now, its histogram, strangely enough, has a kind of smaller range. This one had 7, and this is up to 6. It's because I can't pick the 7 guy twice. So there's kind of without replacement going on here. I also seem to have a lot more data, but what the heck? Let's draw this, but I'm going to use, let's say, that's 6. Do I want 4? I'd like to see a better shape. I'm going to do it by, let's see, 3 up to 6. That's 3, 4, 5, and 6. I can use 3/4. So I'm going to do 3 to 3.75. 3 is in this set. 3.75 to 4.5. 4.5 to 5.25. 5.25 up to 6. Try it that way. All right, so how many 3 up to 3.75? There's 1, 2, 3, 4, 5, 6, 7. How many 3.5 to 4.5? There's 1, 2, 3, 4, 5, but we don't include the 4.5. Now we'll do 4.5 to 5.25, so 1, 2, 3, 4, 5. 3 and 1. Huh. That picture looks a little bit different. It's not quite like that one, is it? Now, what happens if we draw them 3 at a time? Pick 3 from that set, calculate their average, get the data, repeat this, make some histogram. Well, an interesting thing happens. Individuals vary. Groups of individuals vary less. It happens mathematically. Because the groups of individuals, when you average as their data to make a single point, there's less ability to vary. Think of the weights of people. If you have a large man and a bunch of smaller people, when you average them, his value towards that data is buffered by other people. And so if you had a very small piece of data and a very large piece of data, there'd be a heavy variation there. But when you average, since there's nobody else like him, it's pulled down. See this 7? It's pulled down to a 6. And so the variation is going to decrease. Now here's the strange thing, is you take more and more groups of data. The average actually can't change. Turns out this and this have the same average. And here is what we can actually, and we'll later outline a clear proof of. It's the following amazing fact, that when you have a list of data, and you need to make it large enough, population, you sample from that list in groups. Record X bar of that group. Whatever the measurement is, whatever the histogram that this started like, it could be crazy. If we start graphing these x bars, they become normally distributed. And in fact, the variation shrinks as n gets larger, so the variation shrinks. Now, you obviously have to have a large enough data so you can really let n go to infinity, or you're taking groups, you realize. However, the average doesn't move. And here's the next thing that happens, is the curve or the distribution of the x bar for these samples becomes unimodal, symmetric. In fact, it's like a bell shape. And which bell shape does it become? Well, it becomes a specific bell-shaped curve. That specific one is the result of doing a limit. And so there's a good choice for a bell-shaped curve. And that good choice revolves around e to the minus ax squared. This is a function that we're now going to investigate. So let's do that. Let's start with a function f of x equals e to the minus x squared. That's a real simple choice. Turns out when you graph it, it looks something like this. It's maximum at 0. Let's find out what its area under the curve is. So let's integrate e to the minus x squared dx. From minus infinity to infinity. And all of you should go, yes. Should say, I'm not sure I know how to do it. You're right, unless you've had Calc 3. So, it turns out that this integral by no means is obvious. If some of you remember, e to the minus x squared plus y squared dx dy, from minus infinity to infinity, from minus infinity to infinity, which was a truly bell-shaped curve in two directions. Did you remember doing this integral? So it turns out the function that I want to look at is a very hard technical integral. Now, it's actually quite trivial to do in complex variables when you integrate in the complex world, which some of you may take as your senior year. But as it stands right here, there's no real simple way without some mathematical machinery to get an answer. However, let's do our continuous integration trick. Let's not care what the answer is. Let's say, I think it's finite. Well, then we develop a new function, f of x equals 1 over a e to the minus x squared. And just like this can be a probability density function, because its integral will be 1. So it really doesn't matter, it's just so we know that that has a finite answer. That's a tough one. Why is it a tough one? Because it would be kind of nice to know what this value a is. Because it's nice to have an abstraction, but I'm writing down a very specific function. So I'm going to go through the classic Calc 1 trick. And it's not really deep, but it requires you to understand the concept of fundamentally between a variable that is bound over a region and therefore the result takes on a fixed value independent of the name of the variable. And a slight other trick, and that is I have to be able to make sure that these integrals are correct to combine the way I'm going to. So I'm going to begin with the following question. And I'm going to put a number in here to make my life easier. Actually, two very strange numbers. I'm going to call my integral to be minus infinity to infinity of 1 over the square root of 2 pi. That's the first funky number I'm going to put in there. 1 over the square root of 2 pi. And e to the minus, and I'm going to put z squared over 2 dz. Okay, and I'm using z as a dummy variable because I'm going to want to use x and y here as well. So here's an integral I would like to know. I do not know its value. Now, I happen to know that when I square that integral, I have every right to write that integral twice. And I have every right to say, well, this z is the variable for this integration. I shouldn't use it over here. I should use a different variable here. So since that's the original z, heck, I'm going to put a y here and say that's 1 terms of the variable. And now here I'm going to put e to the minus x squared over 2 dx. And so I just chose two different variables so that I have two integrals that are exactly that. But now, if we know that integrals can somehow be combined, it would be nice. Is it possible that the product of these two integrals can be actually done in the following way? We'll put the constants together, we'll multiply these, and we'll say the integral is this way. Now, what's required here is that these variables are varying independent of each other, that the x cannot affect the y and the y cannot affect the x. In order for us to make this step, we need that requirement. And then we can say, oh, I learned this in Calc 2 with polar variables. So I'm now going to switch from Cartesian xy into polar r theta. Now, if you remember, when you switch into polar r theta, the dx dy becomes r dr d theta. And now we have to express, I'm going to put this in front, the 1 over 2 pi. Now we have to express the relationship between xy and r theta, but everyone should know that x squared plus y squared is r squared, and so that means that I can put e to the minus r squared over 2 here, because that's x squared plus y squared is r squared. And now it's a question of if x varies from minus infinity to infinity, and y varies from minus infinity to infinity, how does that explain how r varies? Well, x varying from minus infinity to infinity means right and left. Y varied up and down. It means that we have the entire Cartesian plane to integrate over. Well, that means in order to get out here, we have to have r vary from 0 to infinity. So minus infinity to infinity x and minus into infinity infinity for y requires that r goes from 0 to infinity. And in order to get the whole plane, we can do theta varying from 0 all the way over to 2 pi. So now, that's the requirement that this region be described with the correct limits. So this, now I wrote r dr d theta, so the r should go first, 0 to infinity, theta goes second, 0 to 2 pi. And now you're seeing where this 1 over square root of 2 pi actually originated from. Now, when this integral is complete by substitution, lo and behold, this answer is 1. This is a positive function. Therefore, the only number that squares to 1 that is positive is 1. We have just proved this answer is 1. So now, it is possible for us to work with specific exponential functions. There was that silly 2 in there, and that 1 over square root of 2 pi, and this strange-looking function actually has its integral now equal to 1. That wasn't the function I wrote down in the first place. Challenge question. Go home. See if you remember your calculus enough. If I had started with f of x equals e to the minus x squared, what should my f hat be so that this integral equals 1? And you adjust it. You know how to do that, knowing this fact. Well, this is a very fundamental distribution. It is so fundamental we give it the name the bell curve, probably with a capital T. Also called the normal curve. Also called the Gaussian curve. It's pretty crazy. So, I'm now ready to attack something else. What happens if I mess with this function and ask, can I make a more complicated function that looks like this? One of the things I can do is take and shift this. If I have a bell curve here, if I shift it this direction, that should still be, quote, a bell curve. A normal curve is just centered in a different place. You guys know how to do a shift. Change x to x minus x naught. So it seems to me that I should be able to write down f of x equals 1 over the square root of 2 pi e to the minus x naught quantity squared over 2. That should also be called a bell-shaped curve. Now, this bell-shaped curve, how fat is it? What do we mean by fatness? And one thing might be nice to find these inflection points. What happens if I just squish it right and left? If I squish it, I'm probably going to reduce the area, so maybe I should make it a little bit taller. But it seems to me that I should be able to also do an x changes to an mx and adjust this thing a little bit. Well, lo and behold, I can do both of these. Shift it and squish it, but still keep the area 1 by doing a very simple substitution of the integration. And so this function, f of x, which is 1 over a number sigma, guess what that number means? We'll see. Square root of 2 pi e raised to the minus x minus mu quantity squared over 2 sigma squared. And notice, the mu, that was the shift. This mu here is actually a 1 over mu x substitution, and a sigma ends up in front. This function has the following neat property. F of x integral from minus infinity to infinity equals 1. So, homework to be handed in. Show this using the fact that the integral of e to the minus x squared over 2 from minus infinity to infinity equals the square root of 2 pi. So you need to know that this function is the appropriate algebraic calculus adjustment from a continuous function of this nature. Whoops, I dropped a 2 here, sorry. Of this nature produces this function. This is called a standard normal distribution. We use the symbol n, and we write mu sigma. Now, some textbooks will write standard normal mu sigma squared, and it varies from book to book. So we need to make sure that if we reference it, that we're using our book's own notation. And let's see, did they define that in chapter 3.3? Let's see. Yep, they use this notation. So they write sigma squared. When we use this notation, that means we would never write 3/7. We would always write normal 3 square root of 7 squared, so that we are telling people that we are using the variance form of the notation for the standard normal expression, and we would write the standard deviation squared. We won't write it this way ever when we're thinking of using this as our standard notation. Now, if you were learning from a book that used this notation, it would be acceptable. So our canonical form is we don't write the variance. We write the standard deviation squared to communicate the form that we're using for expressing the distribution. So be warned, we need to do that. All right. Now, since we have some calculus in hand, let's do something fun. Let's do another integral. What's our definition of m of t? It's the expectation of e to the tx. And oh my goodness, the normal distribution that we just looked at is an exponential. So let's use our normal mu sigma squared and find out what the moment generating function is. Now, it should be pretty obvious that if we started with e to the minus x squared over 2, that looks like mu for that one would be 0, so the other ones, we'd fully expect to get mu to be shifted, so we should expect that mu to come out from our m of t very trivially. But the nice thing was what's going to come out from that mu, that moment generating function, what is going to be the variance. And what's nice about that is the m of t is the fastest way to discover using this distribution what is its variance. So this is the expectation. Whoops, I just wrote that. E to the tx. It's the integral from minus infinity to infinity of e to the tx, 1 over sigma, the square root of 2 pi, e to the minus x minus mu squared over 2 sigma squared dx. Now, this is not super rocket science to get these combined, nor is it super rocket science to complete the square. So let me just point out, this is the combination of exponents and completing the square. Now, all of you should have in Calc 2 have gone through this messy calculation. However, I don't think that it's necessarily great or grand to say, let's put this on an exam. But I do expect you to be able to verify algebraically that when I define the m of t this way, I still get my minus infinity to infinity. I still get my 1 over sigma, square root of 2 pi. And all the things that I get extra after that simple steps is a single complicated expression. It is e to the minus 1 over 2 sigma squared. We made sure to keep that denominator. And we get x squared minus 2 mu plus sigma squared t x plus mu squared. And then we have our dx. Now, did I complete the square yet? No, I haven't completed the square, sorry. So now we're going to complete the square. So we'll bring this back in. Completing the square, x squared minus 2 mu squared plus sigma squared tx plus mu squared. When you complete the square, all right, let's get this right. X minus mu plus sigma squared t, quantity squared, minus, and now we need the adjusted parameters, 2 mu sigma t, it's a mu squared sigma t minus sigma to the 4th t squared. So after doing all of this work, we can create this completed squared monstrosity. Well, what does that say? It says that our expectation is going to be a constant, which we can pull out, times a well-formed negative quadratic expectation, which we then can do a standard U substitution to reduce to something we've done before. Well, shouldn't be too hard, but how many symbols do we have? We got 1, 2, 3, 4 symbols, let alone in there besides the pi. We've got a large number of symbols. How hard can it be to finally reach an integral of 1 with a constant in front? Well, you should do the U substitution, or change a variable, to get, and you should do it once. Everyone should do it once. To get m of t equals e and the mu of t plus sigma squared t squared over 2. And this expression makes total sense for t to be any real number. So this m of t is well defined over a large region. Now, once again, this happens simply by making the simple substitution to here to make this all work out nice. By the way, hint, since this is a constant in this, it means it's a product in the exponential, so when you do the U substitution, this part's going to pop out with 1 over sigma squared of 2 pi, and then you'll be working with this guy over e to the minus a new variable u squared, which this is u. So this, by the way, is your u substitution. Those of you that actually go to the time to complete it, this will just pop out, and that part of simplification is where this comes into being. All right, once we have the m of t, that means that for this wild, funky function, so let's write it down again, the wild, funky function, sigma over the square root of 2 pi e to the minus x minus mu squared over 2 sigma squared produces an m of t, which is e to the mu of t plus sigma squared t squared over 2, which then says that m prime of t, well, we can take the derivative. You always get an exponential function back. Now times the derivative of the exponent. Mu of t's derivative is mu. Sigma squared t squared derivative is sigma squared t. That means m prime of 0. Well, we put in 0 there, it's 0. E to the 0 is 1, 0 there is 0. We get mu. And lo and behold, what we expected to happen was that the shift of the standard normal distribution, 0, 1, when moved to a mu location, has an average of mu. That's nice to know. Well, what's the variance then? Well, let's move forward. The variance is m double prime of 0 minus mu squared. So now we need to take the second derivative. Well, the second derivative of this one worked out quite nicely. It has the same mu of t plus sigma squared t squared over 2, except now that when we take this derivative, the expression gets a little bit more complicated. For those of you that have done enough exponential derivatives, that you happen to know that the structure is going to repeat itself. So a linear is going to come in front, and we already have a linear there. When simplified, it's going to actually become a quadratic. And that quadratic is mu sigma squared t quantity squared plus sigma squared is what ends up in front. Now, let's evaluate this. Well, when those values are plugged in, the variance of x is mu squared plus sigma squared minus mu squared. If you notice, this goes away, and there's your sigma squared. You get sigma squared. Hence, the reason that this is called normal mu sigma squared. Its average is whatever number you find there. Its variance, as long as this looks like that, you've identified the variance and the standard deviation. Huh. That's curious. Now, what's also very interesting is just to take a look at, if you were to graph this yourself, what happens in this graph. Wouldn't it be neat if the following was known? That the inflection points here, wouldn't it be neat to know where they're located? Do you think they're structurally easy to find? The answer is yes. Wouldn't it also be neat to know what some of these areas are? And the answer is yes, because it turns out some very nice things happen. All right, I'm going to leave you there because it's a good amount, and I'm going to pick up on the standard normal distribution values by doing its CDF. It's cumulative distribution function. So now we have this thing. We're going to look at some properties, and we're going to discover what some areas under the curve look like. At that point, the next lecture is highly numerical, and we will be making use of tables. Those of you who have calculators, you have to be able to find the cumulative distribution function values on your calculator, or I'm going to be handing you a copy of the end of your book, which we're going to do next time. When you have an exam, you're going to be given a different part of your book than you were given the other time, and that part of your book is some tables of well-known values. First off, you have your binomial table, quite long. You have the Poisson table, not that long. Then you have the chi-square table. And the chi-square table is all gamma distributions. That's why we can get away with one table using that. And then comes the standard normal table, and there's two ways that it's used. This one is the CDF, it's the area up to as a point, and here is the complement CDF, the 1 minus the value. And so if you compare these two tables, this table's value is 1 minus is over here, but it actually puts other values in the table, and we'll discuss that, how to use these tables. Now, some of you do have a calculator that has some named functions. So it would be kind of nice if this function and its CDF had some standard names. I will pick up on that next time looking up the different ones. One of them is called the Gaussian. Another one is called the error function. The other one is called the normal CDF. We need to talk about what they mean and how they evaluate to the specific integrals at hand, because we're going to want values. I find it very strange that after all this time in the mathematical world, that we have this wonderful theory of functions where there's one integral that gets answers, but what the problem is, we're going to discover is the areas under a curve up to a certain point fails to have a closed form solution. It's just like the log of 7. What is it? Do you know? You can describe it. What's its answer? Oh, you don't have a formula for log of 7. You have a picture. This is the same thing. Well, we have log 7 on our calculator. Why don't I have this answer on the calculator? I find that very strange. We should be pushing that this is a standard function that can easily be found on every calculator. Plug it in and say, here's my number. The slight complexity with that is the logs could have log base 3, log base 8. So you have log a of x. That's not too terribly bad. This function, however, is the CDF of the normal mu sigma squared at some point z naughts. You've got to get 1, 2, 3 things put in before it gives you an answer. And this one requires one thing and a second thing to put in, so it's slightly more complicated, but unfortunately not commonly found on calculators.